Hello! I would like to explain how to do assignment number 5. So the first thing you're going to do is open your physics notebook and scroll all the way down to the bottom of the presentation, and that's where you'll find slides that I added to your Google slide. And those are the ones that you'll need for this assignment. So the physics notebook can be accessed on the classwork tab under physics notebook, and just a reminder, I did make a physics notebook originally, and then after I learned how to use the program where I can add Google Slides to your presentations, I had to create a new physics notebook. So we're going to transfer things that we did in the first one to our new one. Alright, so the physics notebook should look like this. Well, by the time you're done, it should look like this. The first thing you're going to do is fill out the table of contents, and you can click on the new link to the sample notebook here. So you might already be linked to a sample notebook, but just make sure that it is the one that is linked here. Alright, so this is the table of contents, and we're gonna order our notebook by entry number. So entry number 1 should be the collision predictions, and in the slides that I added, I created a new one for you in case you couldn't figure out a good way to format it before. If you'd like to use this, you'll see that like on the sides, there's draggable images that you can use to fill it out. But if you already did it before on your other notebook, just copy the slide. So click on the thumbnail of the slide, which would be like this, Control-C, and then Control-V into your new notebook. So that's going to be entry number 1. Entry number 2 is the collision simulations. And again, that was the one that was assignment number 2. So if you already did it, just copy it over onto your new notebook. Alright, now entries number 3 and 4, those are the ones that I'm checking for assignment number 5. So entry number 3 is a set of notes on collision and conservation of momentum. So here it is. The way that you fill this out is you're going to click on this link to open up this website, and you're going to fill out these notes. Like anytime there's a question mark, you're going to replace that question mark with the note. So for example, the first one, momentum, and then is the term, and then what is the variable for momentum? Well, if you look at this web page, then you'll see it's almost a replica of the website. I changed the wording a little bit, but you would just write P. And you'll do the same thing for the others. Down here, like within a system, momentum is question mark. And it's not completely obvious like where that answer is in the website, but it's kind of by design because I want you to read. So it says momentum is conserved. Or it also says it here. Within a system, momentum is conserved. And then, let's see, on the sides, you'll see it says drag to label, and you'll just click on the image and then you'll drag here. So we have a few different equations, and each one can be used for a different set of collisions or explosions, and you will see that here, as you read, you'll see the different types of problems have different types of equations. So for this first one, or for this one, we have an initial velocity that two masses are undergoing together. And then after the collision, or in this case, it could be an explosion, or if you were throwing something away from you, like you're standing on a skateboard, you're holding on to a mass. So it's like mass 1 would be you, mass 2 would be the thing that you're holding. And then after the explosion or throwing, the two masses are going to split. So we want to know the velocity of your own mass and then the velocity of the thing that you threw or the object that got exploded from. So here are two visuals for that. So you'll read through, read about each equation, and then you'll fill out the bottom where it's talking about terms. So M2, what does that stand for? V1I, what does that stand for? So just fill out that chart. And the next part is the practice problems. So the instructions are listed up here. On the document itself, let's see if I can, there we go. On the document itself, you're going to highlight all of the givens in the problem. So you can just click and highlight. Then you'll draw a simple picture. You don't have to draw the actual objects. You can represent them like with boxes or circles, something like that. And you're just going to show before and after. So what is the situation before the collision or explosion or action of throwing something, and what does it look like after? The key things there would be you want to have the object, and then you want to have the velocity, which includes magnitude and direction. So make sure you include that in your label or your picture. Next is just completing the problem. So you'll write out the equation that you'll use and then solve, and you need to show all of your algebraic steps along the way in order to earn credit. I recommend doing this on a piece of paper just so it's not annoying trying to show your work on a Google slide. If you have a tablet or something, you can go ahead and use that, but I don't recommend doing it on this slide unless you have a lot of patience. So I do recommend if you write it on a piece of paper, you could like fold that paper in half and write out your answers to the problems. You don't have to write the problem. And then make sure you number the problems. And then if you take a picture of that column, so if it's folded in half, hot dog style, then you could insert the image here. And you insert images by this. So you would have to upload it from your computer. Or if you want to use your webcam, you can even just click on camera while you're in the document and take a picture of your work from there. Alright, so the next part of this video, I'll show you how to do one of the problems. The conservation of momentum practice problems are in your physics notebook and should be set as entry number 4. So there are 7 problems, and I'm going to do the first one with you. A 0.8 kilogram firecracker is traveling through the air at 12 meters per second to the right when it explodes. After the explosion, a 0.3 kilogram piece of it is flying to the left at 6 meters per second. What is the mass of the other piece and how fast is it flying? For this assignment, you need to draw a picture and highlight your givens that are in the problem. So I have my before information highlighted in blue, or I will have it highlighted in blue, and then the after information highlighted in green. So the firecracker starts out as just a single object, 12 meters per second to the right. And after it explodes, it becomes two objects. One of those objects is 0.3 kilograms, moving 6 meters per second to the left. And we're looking for the mass of the other piece, and we also want to know how fast it's flying. So here's the single firecracker, and then here's the firecracker split apart. In conservation of momentum problems, the key idea here is that momentum is conserved, and so the initial momentum is equal to the final momentum, and we'll use that knowledge to help us solve for any unknowns. So what I'm going to do first is just figure out what the momentum is initially. Since there's only one mass and one velocity, all we have to do is multiply those together. So Pi equals mass times velocity. And it's just 0.8 times 12, and I get 9.6. I guess I should use the time symbol so that it doesn't look like decimals. All right, so 9.6, and our units are kilogram meters per second. All right, so our total momentum before, I'll just rewrite it down here. So 9.6. Yeah, I draw my numbers so far apart. Let me try that again. It still looks super far apart. Kilograms times meters per second. And this is our total momentum before the explosion. Now, let's find the momentum after. So the momentum after is it consists of the momentum of two objects, and we're gonna add their individual momenta together. So I'm just gonna start off by figuring out the momentum of that first mass. So we have 0.3 is the mass, and we're gonna multiply that by -6. Because that's its velocity. So I get -1.8 meters per second. So that's one of the momenta. And now we gotta find the other one. Now let's look back up at these equations. So the equation that we want to use would have a velocity, like just a single velocity multiplied by a combined mass. So that would be this third one, or I mean, it's the third equation down. And I think I don't know why I wrote V1 there. I should have just written V. So you can pretend that this doesn't exist. But it's just showing that there's just one velocity for both of the masses combined. And then after, so that it's like before equals after. So after we have mass 1 times velocity 1 final, and then mass 2 times velocity 2 final. so far we have figured out the whole first part of the equation. We figured out the first part of the second half of the equation, and now we just need to figure out this. So if you wanted to just plug in all of your values to the equation at the beginning, you could have done that to solve for it. But this way you kind of think through like the process rather than just immediately plugging it into the equation. So let's see. There is a little bit more that we could figure out regarding the mass. So if we know that our total mass is 0.8, so our total mass is 0.8, and then 0.3 broke off, then we can just, calculate the remaining mass would be 0.5. So 0.5 plus 0.3 is 0.8. All right, and now we just got to find the velocity. So I'm going to write out my equation, like initial velocity is equal to, initial momentum is equal to final momentum. And then the final momentum, so the final momentum is equal to, I'll say, I'm going to call this momentum 1. I'll just say P1F plus P2F. So P1F, P2F. And now let's start plugging some things in. So we know that our initial momentum is 9.6. We know P1F is negative 1.8. You know what? I'm just going to leave the units out so that it's a little bit clearer. So we have 9.6 equals 1.8 plus now P2F. We have mass, it's 0.5, and then we have to multiply that by velocity. So we'll just call this V2F. All right, so we can't combine those because this first, wow, a circle. This first number is not attached to any variables, whereas the other one is being multiplied by something. So we cannot combine those two. So what we can do is add 1.8 to both sides of our equation. So now we get 0 there. $11.4 is equal to 0.5 V2F. Our final step would be to divide by 0.5, and I get 22.8. Let me move this over, and let's see, and then what is 22.8 equal to? Like, what did we just solve for? Well, we solved for the velocity to final. So this is going to go up to right there. And since it's positive, we know that that means it's going to the right. All right, so now we want to figure out if the initial momentum is equal to the final momentum. We just want to verify that. So, well, technically, at this point, you solved the problem. So you could just turn it in. Yep, I found the mass and I found the velocity of the second object that split from the original firecracker. And I'm just going to show you that the initial momentum is equal to the final momentum by just, let's see, I'm going to calculate the momentum really quick. So the momentum of the second object would be 0.5 times 22.8. Did I write that earlier? Oh, yeah, whoops. Since I didn't include units earlier, my bad. So this, we would end up having just meters per second here. And the reason why is because we'd end up having kilogram meters per second divided by kilograms, and then that would cancel out and we'd end up with meters per second. So there you go. Anyway, so our final momentum for mass 2 would be 11.4. And if we calculate the total momentum for those two things, to get the total momentum after, we would get negative 1.8 kilogram meters per second plus 11.4 kilogram meters per second, which is equal to dun, da, da. Oh, I mean in green. Whoops. Okay, let's try that again. Dun, da, da. The final momentum is equal to the initial momentum.